Hi, I'm Steve Tuecke. I am one of the co-leads of the Globus project. So Globus is a project out of the University of Chicago that is focused on providing research data management software to the scientific community. And my role is one of the project leads, or we're a strange little group because we're actually trying to build essentially a sustainable nonprofit company in the university with what we're doing. So if I phrase it in those terms, I'm basically the CEO and CTO of Globus. So scientific computing is a value for a lot of reasons. So I've been in this area for about 25 years now. I started at Argonne National Laboratory, which is one of the main DOE science labs, back in the late 80s as an undergrad on an internship, and have really been in scientific computing ever since. And what we've seen happen is that in the early days when I was here, it was scientific computing was really only in the physical sciences, in the climate modeling, physics, things like that. And what's happened, it's become pervasive everywhere in the biologies and even into the humanities and other scholarship. And it's so fundamental for really two big reasons. One is all of the data, right? Data, of course, big data is the thing now. And it really is true. It's kind of washed over all these areas of science and humanities such that to do research, you have to deal with big data, which means computing. And second is simulation and modeling. All of the computation needed to model interesting physical systems or organisms at very large scale is absolutely fundamental now to science being done. And so as computing people in science, we've become a really key part of the scientific endeavor. So I'm kind of a polyglot when it comes to science, right? I really love science in general, but I'm a computer scientist, right? I was a math computer science undergrad. And so for me, I really love just being around the scientific community and providing software to a wide variety of sciences. We started in the 90s more in the physical sciences. Our software is in the processing for the Large Hadron Collider, which of course had the big Higgs boson discovery recently. But we also do software for biology and material science, lots of different areas. So it's for me, the fun is really just being involved with all of these really great, smart people doing all this really interesting work across a lot of different areas of science. So my most memorable technical challenge was actually in 1995 at Supercomputing 95, which is one of the big industry conferences and trade shows in supercomputing. And this was back in a time when scientific computing was really just coming into sort of the center of science. And the notion of using supercomputers and high-speed networks and even virtual reality devices was all kind of a lot of really interesting research happening. So a group of us for Supercomputing 95 did this crazy experiment where we basically went out and got all of the open supercomputing centers in the country connected via experimental high-speed networks, which at the time were OC3, 155 megabit networks, and connected this all to virtual reality devices on the show floor and managed to get 60 scientific applications to come in and try and show what they could do on this thing. And it's called iWay, and there's a really good paper out there about it that describes this, but it really was what galvanized the community to go into this whole area of scientific computing and NSF funding for it. And it even worked at a few instances in time. There's a ton of challenges in scientific software. The underlying issue in some sense that we're trying to deal with in Globus is that software for science is frankly pretty bad often, right? It's a small, fickle market. There's not a lot of money to be made here. And so as a result, there's not a lot of software actually created for the scientific community or commercial software for it. So it's a lot of homegrown stuff, a lot of other, cobbled together solutions. And so what I see as one of the big challenges for science and software for science is how do we actually put in place models to provide very high quality, commercial quality software, with the same sort of quality that we see in tools like Facebook and Gmail and other sorts of software that we see in our consumer lives and that the commercial world sees in their companies. How do we bring that into the scientific realm so that scientists have the high quality IT that's there for them, so they're not spending all their time wasted on IT, but doing it on the process of discovery? As a new student going into scientific computing, My main recommendation would be to get a very broad exposure to both math and science, right? If you look at some of the trends right now in scientific computing and in computing in general, right, is that, of course, data science has become a huge thing now and is really, again, with all the data hitting science and scholarship, being able to do really good data science, data analytics is fundamental to a lot of what we need to do going forward in scientific computing. So getting a very strong math and statistical background for that. On the other end, all the computing side, right? There's all this really interesting stuff happening in the computing world around cloud computing and how you apply that to problems, and parallel computing, machine learning, right? So getting a broad computer science exposure as well, even if you don't intend to be sort of a programmer in the commercial world, having that strong programming and math background will be absolutely fundamental to being able to bring that to bear to the science world and really contribute to scientific discovery.